So I'm interested in how the brain controls food intake and body weight with respect to appetite. And I'd like to share with you some of the findings that I produced during my PhD, which looks at a new peptide called humipressine. And I'll show you how it affects feeding behaviour. Now, as I'm sure you're all aware, appetite affects 1 in 3 people in today's affluent Western society. But it's such an issue because the associated comorbidities such as diabetes, stroke, cancer, if obesity is not dealt with in the next 10 years, it's set to bankrupt World Health Organisations. Now, obesity is such an issue because it's got such a complex neurology. Because it's so complex, it therefore is incredibly difficult to treat. So I believe that obesity is a product of eating too much, and therefore I think that the answer lies in our appetite. So appetite is defined as the brain's balance between hunger and satiety, which is like the feeling of fullness. It can be crudely split into 2 parts. Those which are homeostatic, such as the need to eat, and those which are hedonistic, such as the desire to eat. And I believe it's this later aspect that underlies the current obesity epidemic. So here we've got an example of a primarily homeostatic stimulus. So we take rats during the daytime when they're normally asleep, with an injection of 2-deoxyglucose or 2DG. We see that this increase in feeding behaviour. Now this is because 2-deoxyglucose tricks the brain into thinking that sugar levels are low, and therefore in an attempt to reassert homeostasis, we see this counter-regulatory increase in feeding behaviour. But if appetite was controlled exclusively by homeostasis, we'd all be at our ideal body weight. And we know this isn't the case because we know that humans and animals go to great lengths to obtain palatable food and often eat beyond this homeostatic need. So here we've got an example of a hedonistic stimulus. We would take rats during the night time when they're normally awake, and we give them medium-sized meals so they're partially satiated or partially full. We then inject them with THC, which is the active ingredient of cannabis. We see that the rats get the munchies and increase in food intake, even though the homeostatic need to eat is already there. So the neuronal circuitry underlying these effects is incredibly complex. And just to give you a bit of a brief introduction, so here we've got a sagittal MRI scan of the human brain and a schematic coronal section. So this is just a slice straight down from the front. There's little doubt of an integral role played by an area of the brain called the hypothalamus. Now the hypothalamus is in such a position that it can send signals such as glucose and leptin to the blood, and it's known to coordinate important feeding responses. Impinging on this hypothalamic control of feeding behaviour, you've got areas such as the striatum and the prefrontal cortex, and these areas impinge aspects of reward, motivation, and food preference. These impinge then on the hypothalamus integrates this information and outputs to the rest of the body to either start or stop eating. So one way to manipulate this system is to think, well, what do all these different aspects of appetite share? And the one thing they share is they all communicate with each other via the endocannabinoid neurotransmitter system. So endocannabinoids are primarily based on 2 lipid agonists called anandamide and 2-AG. And they bind to the cannabinoid 1 receptor, which is found in the brain. So because these are agonists, they'll bind to the receptor, and this will initiate a response in the following cells, and it will propagate these aspects of motivational appetite. So again, if we administer a CB1 agonist to pre-satiated rats, again, like with THC, we see this increase in hedonic motivation to eat. So if we can devise something that acts in the opposite way, that instead of binding and activating the receptor, it block the receptor, we hopefully see a significant decrease in food intake, and this could be a potential cure for obesity. So the majority of my PhD was looking at this peptide called humipressine. Now, we discovered humipressine to naturally exist in the bone fluid. However, the only thing we knew about it was that it bound and antagonized and blocked these CB1 receptors. We knew nothing about how, where, or its biological role in the body. So because it antagonized these CB1 receptors, the obvious question for me to look at was, well, what is its effects on feeding behaviour? So I administered humipressine directly into the brain of mice, and we see we get a significant decrease in feeding behaviour 2 hours post-injection. Furthermore, if we repeat this with a systemic route of administration, so this is just into the periphery, such as if you get a jab from the doctors, again we see a significant decrease in the hedonic motivation to eat 2 hours post-injection. Importantly, if we repeat these experiments in mice that do not contain functional CB1 receptors, these effects are not seen. So this suggests that humipressine travels in the body, crosses the blood-brain barrier, where it activates and blocks central CB1 receptors within the brain. So again, hemopressin has an effect on food intake, but again, we know nothing about where or how it acts. So to address where hemopressin acts, we can use a technology called imaging mass spectrometry. And this basically scans the rodent brain, and it will tell you exactly where peptides are localized dependent upon their size. So before I show you the results of hemopressin, I think I'd like to just share what we'd expect to see for, say, the CD1 agonists that I described before, such as anandamide and 2-AG. If we were to do this experiment, we find that these ligands are found throughout the rodent brain. However, quite remarkably, when we look at hemopressin, we see specific localization here, just in the hypothalamus. So again, this is a rat neuronal brain section. This is also confirmed using functional magnetic resonance imaging. So this is a technique that will show you which part of the brains have been activated in response to a drug. And again, we see specific localization here in the hypothalamus. So this suggests that hemopressin is affecting food intake and is in prime position because it's localized within the hypothalamus. So I've shown the existence of a novel neurotransmitter that is capable of modulating the homeostatic and hedonistic aspect of appetite. And this is incredibly important for future and treatments. Thank you.